right, 10.4. What we need to do is to prove some results about regular polygons and also introduce some language so that later on in the next section, we can prove the the regular polygon area formula. And then on the basis of that area formula, derive the area formula for a circle, though perhaps I should not say derive. The story that I will tell about circle area formula I don't think really rises to a strict derivation, but I can certainly give you the flavor of that, and that will be based upon the regular polygon area formula. All right, so a little bit of terminology. We say that the center of a regular polygon is a point in its interior equidistant from its vertices, and we say that a segment from the center to a vertex is called the circumradius, as you see in the diagram. We have a regular hexagon, a point C that is its center, and then the segments from that center point to the vertices are all equal in length. Now, as has been stressed multiple times in this class, that I have provided a definition of a term does not imply that any object actually exists that satisfies that term. Think, for instance, of the example of unicorn. I can define that term, at least roughly, but that doesn't mean that unicorns exist. So one of the problems that's in front of us then is to actually prove that a regular polygon does have a center. And this will be done in the problem set. You will see, perhaps the last time of the year, probably the last time of the year, a column-style proof on the worksheet. I did this because the proof is rather long, it's multi-part, and I wanted to make sure that you were on track throughout it. So I've done what I used to do, that is I provided statements and you will provide reasons. So next term, apothem. An apothem is a segment that goes from the center, which by the time you reach anything about the apothem on the worksheet, you will have proven the center exists. The apothem goes from the center point out to a side perpendicular to the side. So in the diagram, C is the center. And then we have gone from that center point out perpendicular to a side, and that is the apothem. And of course, a regular polygon has multiple apothems, one for each side. And you will prove various results about apothems and circumradii as well. As I've said, you will prove that every regular polygon does indeed have a center. You will prove, as expected, that every circumradius bisects an angle. You will prove that each apothem bisects a side, and once again, we have one apothem per side. And finally, you will prove that all apothems are equal in length. So here's part of what you will prove in picture form. You will prove that each of the circumradii bisects an angle, as is marked. And you will also prove that each apothem bisects an angle, and they're all equal in length. So you can see I've constructed in all the apothems in this case, all the right angles are present. And each apothem bisects a side, and each of those apothems are equal in length. Now, I've also noted as well in the diagram that since all the sides were equal, since by definition this was a regular polygon, or since by stipulation this was a regular polygon, then all of those pieces, all of those halves of the sides created by the apothems are equal to one another. Now, how will all these proofs go? Well, triangle congruence, of course, right? So what you should expect is that you'll draw in all the circumradii and you'll draw in all the apothems, so you'll have all these right triangles and you'll be able to prove them congruent to one another, and you'll be able to prove the congruences, as it were, as you spit around the center point. It's not that difficult, honestly, though it goes on for a while, and you will see it in two-column form. And I think this is the last use that we make of congruence in this class, which makes me a little sad because congruence is one of the primary tools of the class. Now, note a result that will follow immediately once you've proven that a regular polygon has a center, defined as the point equidistant from its vertices. What this means is that if we begin to construct a circle whose center is the center of the regular polygon and passes through one of the vertices, then that circle must pass through all of the vertices as well. Now, do recall that we have a circle existence postulate, which says that if a center point is provided and a radius length is provided, or if you like, a second point is provided, then we may construct a circle with that center point that passes through that second point or has that given radius. So what you're to imagine in this case then is that you have a regular polygon, you have its center point, and then you construct a circle with that center that passes through one of the vertices. So at this point, the circle is defined. It has its center point, it has a point on the circle, so the circle is defined. And then that circle must pass through automatically, as it were, all the other vertices, because all those vertices, as you have proven, are equidistant from that center point. So to put it simply, what that means is that every regular polygon is inscribable into a circle. So here's an example. So let us say that we began with the regular triangle, ABC. We know, or will know, once the proofs of the section are complete, that a circle does exist that passes through all of the vertices. Now, what can you do with that? Well, here's the sort of thing that you can do. Mark the center of the regular polygon. So we've got the regular triangle inscribed into a circle, and it could have been a regular polygon of any number of sides. What I'm about to say will be true for them all. And what do you do to get relationships between the circle and the polygon? Well, typically what you do is this, is you drop in an apothem, which splits a side in half, and then you also draw in a circumradius, which splits an angle in half, which in this case will split a 60-degree angle in half, so you'll end up with a 30, 60, 90. So, for instance, if r represents the radius of the circle, then, well, let's see, that's the hypotenuse of the right triangle, which means that the side opposite 30 is r over 2, and then the side opposite 60 is r root 3 over 2, which means the entire length from A to B is double r root 3 over 2, which is simply r root 3. So that's a nice little relationship. So if you have a circle circumscribed about a regular polygon, that is, equivalently, a regular polygon inscribed into a circle, the side length of the regular polygon, well, triangle, is the radius of the circle times root 3. And you can do this for any number of sides. It's a powerful technique.